You know the frustration of packing for a long road trip, stuffing your car so full of luggage you barely have room left for the actual passengers? Now, imagine if 85% of your car's entire weight had to be just the gasoline required to get you to your destination. This agonizing reality has a name in aerospace engineering: the tyranny of the rocket equation. To get 1 pound to Mars, you need thousands of pounds of fuel. For 70 years, humanity explored the cosmos using the exact same mechanism. We mix fuel, add an oxidizer, light it, and ride the controlled explosion. But chemical combustion has hit an unforgiving physical ceiling. Despite decades of massive research, we have squeezed almost every drop of performance out of this technology. The maximum theoretical efficiency, known as specific impulse, tops out right around 460 seconds for our absolute best chemical engines. Trying to reach the outer solar system on chemical rockets is like trying to cross the Pacific Ocean in a rowboat. You can, but it takes forever. So, the core intellectual question that has kept aerospace engineers awake at night since the dawn of the space age is a stubborn paradox. How do we move heavy payloads across the vast ocean of the solar system fast enough to survive without turning our ships into giant gas tanks? When most people hear the phrase nuclear rocket, panic immediately sets in. The mainstream understanding of this concept relies heavily on two completely inaccurate extremes. The first misconception is that we are launching a floating Chernobyl, an active, volatile nuclear reactor that could catastrophically detonate over a populated city. The second misconception is even wilder. People imagine we are literally dropping nuclear bombs out the back of a spaceship and riding the destructive shockwaves into orbit. While that was a real, highly classified concept in the 1960s known as Project Orion, it is absolutely not what space agencies are building today. Furthermore, many space enthusiasts confuse this emerging technology with radioisotope thermoelectric generators, or RTGs, which are completely different slow decay systems altogether. RTGs are the long-lasting nuclear batteries currently powering the Mars rovers and the Deep Space Voyager probes as they drift through the interstellar medium. Those RTGs barely generate enough electrical power to run a standard kitchen microwave. They are completely incapable of producing the thrust needed to move a spacecraft. The reality of modern spaceflight is that a nuclear thermal rocket fundamentally cannot undergo a catastrophic nuclear explosion like a traditional bomb. A true nuclear detonation requires incredibly pure, highly enriched weapons-grade material to be compressed in a mathematically perfect microsecond implosion. The physics of the specific fuel we use for spaceflight, combined with the rigid geometry of the engine core, strictly prohibits that runaway chain reaction. In a modern nuclear thermal rocket, there is no apocalyptic explosion, and there are no dropped bombs. There is only intense, perfectly controlled thermal expansion. This fundamental misunderstanding of spaceborne nuclear energy brings us to DRACO, the demonstration rocket for agile cislunar operations. DRACO is a massive $300 million joint venture between DARPA, NASA, Lockheed Martin, and BWX Technologies, with a hard deadline to launch by 2027. The DRACO mission is entirely built around an architecture called nuclear thermal propulsion. It aims to completely rewrite the rules of orbital mechanics. Instead of burning liquid fuel with fire and oxidizers, nuclear thermal propulsion uses a highly advanced, miniaturized fission reactor to generate immense heat. The system takes liquid hydrogen, which happens to be the lightest element in the universe, and violently forces it through the reactor. As the cryogenic hydrogen passes through the intricately designed, glowing hot channels of the reactor core, it absorbs the immense thermal energy almost instantaneously. The liquid hydrogen rapidly flashes into a superheated, highly pressurized gas, expanding violently out the back of the engine bell to create powerful forward thrust. There is absolutely no fire. There is no chemical combustion process occurring anywhere in the engine. It is pure, unadulterated, nuclear-heated thermal expansion. Because hydrogen molecules are incredibly light, they can be expelled from the engine nozzle at terrifying velocities, resulting in a staggering leap in efficiency. DRACO's nuclear thermal engine is expected to achieve a specific impulse of roughly 900 seconds. That is exactly double the efficiency of chemical rockets. In automotive terms, mastering nuclear thermal propulsion is the exact equivalent of suddenly inventing a sports car that gets twice the gas mileage but drives twice as fast. By completely stripping away the heavy liquid oxygen oxidizer that chemical rockets desperately need to burn fuel in a vacuum, DRACO frees up enormous mass. This precise definition, replacing combustion with pure nuclear heat, solves the tyranny of the rocket equation, allowing us to carry massive payloads with less propellant. But translating this elegant physics concept into a functional spacecraft is an absolute engineering nightmare, riddled with extreme material constraints and high-stakes thermodynamics. During the Cold War, NASA actively tried to build a nuclear thermal engine under Project Nerva, but the sheer thermal stress literally melted the materials. To succeed where Nerva failed, DRACO relies on a specialized proprietary fuel matrix known as high-assay low-enriched uranium, or HALEU. HALEU is enriched between 5 and 20%. That is high enough to generate incredible power, but low enough to avoid strict weapons-grade proliferation treaties. The environment inside this reactor is incredibly hostile. The core must survive operating temperatures exceeding 4,400 degrees Fahrenheit without melting. That temperature is significantly hotter than the melting point of almost every known metal, requiring exotic carbon and tungsten composite structures to survive. Simultaneously, one side of this exact same engine is being blasted by deeply cryogenic liquid hydrogen stored at -423 degrees. The extreme temperature gradient across just a few inches of material creates microscopic thermal stresses that want to tear the physical structure completely apart. If that wasn't hard enough, engineers must also combat the invisible menace of hydrogen embrittlement, a phenomenon that destroys metals from the inside out. Hydrogen atoms are so unbelievably small that they literally slip between the molecular lattice structures of the metal alloys, wedging into microscopic gaps. Once trapped inside, the hydrogen causes the once flexible alloys to become incredibly brittle, eventually shattering under the immense pressure of spaceflight. Beyond the metallurgical nightmares, there is the strict safety protocol required to convince the public to actually put a nuclear reactor on a rocket. To prevent any chance of a launchpad disaster, the DRACO reactor is launched completely cold. During liftoff, it is essentially just a harmless lump of metal. The nuclear fission process is strictly locked out. The reactor only initiates its first chain reaction once it reaches a stable, safe orbit above Earth. For all its futuristic sci-fi glory and incredible efficiency, nuclear thermal propulsion suffers from one critical, fatal flaw that prevents it from replacing all rockets. That flaw is its thrust-to-weight ratio. While nuclear engines are unimaginably efficient at cruising, they are absolutely terrible at providing sudden, massive bursts of raw power. A legendary chemical rocket like the massive F-1 engine used on the Apollo Saturn V had a thrust-to-weight ratio of nearly 100 to 1. Those engines could literally lift 100 times their own weight off the launch pad, fighting Earth's gravity with millions of pounds of brute explosive force. In stark contrast, a dense, shielded nuclear thermal engine has a heavily restricted thrust-to-weight ratio, hovering somewhere between 3 to 1 and 10 to 1. This is where the entire concept breaks down. You fundamentally cannot use a nuclear thermal rocket to launch anything directly off the surface of the Earth. If you tried, the heavy, dense nuclear reactor would just sit there on the launch pad, screaming hot but entirely incapable of lifting its own immense bulk. Nuclear thermal propulsion only works effectively in the frictionless vacuum of space, far away from the punishing gravity well of a planetary surface. This means that, despite their incredible technology, we are still entirely dependent on traditional explosive chemical rockets to do the heavy lifting of reaching orbit. We will always have to rely on conventional boosters to carefully lug these heavy, cold nuclear engines through the atmosphere before they can be activated. Nuclear propulsion does not replace chemical rockets, it completely relies on them. The concept fundamentally fails if forced to operate within a planetary atmosphere. So, if these engines are so heavy and complicated, why are the military and NASA pouring hundreds of millions of dollars into launching DRACO by 2027? For DARPA and the Department of Defense, it is all about extreme agility and survival in the new frontier of space domain awareness. Right now, expensive military satellites are essentially sitting ducks. If an adversary launches a weapon, chemical satellites simply do not have the fuel capacity to dodge. Maneuverability in Earth orbit is currently a zero-sum game. Every single time a satellite moves, It permanently burns precious fuel that it can never get back. But a nuclear-powered spacecraft changes the math. It can rapidly and continuously maneuver across cislunar space, dodging threats at will without running empty. For NASA, the real-world application is entirely focused on human survival during deep space exploration, specifically the monumental challenge of sending astronauts to Mars. Using our best chemical rockets, a traditional transit to Mars takes anywhere from 7 to 9 agonizing months, depending on planetary alignments. During that long transit, astronauts are heavily exposed to deadly cosmic radiation, solar flares, and the physiological degradation of prolonged microgravity. Nuclear thermal propulsion possesses the sheer power to cut that dangerous transit time down to an astonishing 45 to 90 days, changing the risk profile. By flying twice as fast, we drastically reduce the total radiation dose the crew absorbs, ensuring they arrive on Mars strong enough to do their jobs. DRACO is not an abstract science experiment. It is the tactical high ground for the military and the fastest, safest chariot to the Red Planet. Engaging deeply with the DRACO mission forces us to radically reconsider our complicated historical relationship with nuclear energy and the power of the atom. Down here on Earth, we primarily associate the word nuclear with the ultimate destructive potential, a weapon fundamentally capable of ending civilizations in a flash. But out there in the freezing, endless void of deep space, that exact same atomic physics flips from a terrifying destroyer to our greatest potential savior. The stark reality is that without harnessing the atom, humanity is essentially trapped in our local cosmic neighborhood, permanently bottlenecked by chemical combustion. The solar system is simply too vast, and planetary gravity is simply too strong for us to conquer it using the same fire cavemen discovered. To become a truly spacefaring species, we have to collectively mature enough to safely ride the raw, fundamental power of the atom out into the dark. So, I pass the question to you. Would you feel safe living on Earth knowing nuclear reactors are constantly being launched into orbit, even cold? Let me know your thoughts in the comments below, as this massive aerospace debate is only going to get louder as we approach the 2027 launch. If this video changed how you view the future of space travel, hit the like button and subscribe to Beyond Delta V for more technology deep dives.